We now talk about design for testability techniques. Well, design for testability generally says some design principles of guidelines that makes the problem of testing easier. There are many such methods and techniques available, but here in this lecture we shall be concentrating on one of the most widely used and popular techniques, which is targeted towards the testing of sequential circuits, which inherently is very difficult. So, the title of our lecture here is Design for Testability. Okay. Let us try to understand why we need this. Design for testability, or DFT in short, as I had said, this constitutes of a set of design techniques or rules that makes both test generation and test application easier and also cost effective. So, as I had said that here we primarily target the problem of testing sequential circuits, because I mentioned earlier that in a sequential circuit, because of the presence of the internal state variables, the flip flops, the number of possible input combinations can be even larger than combination circuits. Not only the primary inputs, but also the state variables. You have to consider all possible combinations of them. There can be so many possible input combinations that may come to the input of the combination circuit part. Okay. So, and because flip flops are inside the circuit, from outside it may not be so easy to initialize them to any known values. We call it control and observe. The DFT techniques, particularly the one that we will be talking about, will make the flip flops easily controllable and observable. Controllable means you can initialize them to any value you want. Observable means we can read out the value of the flip flops whenever we want. Okay. So, the most important thing that we gain out of this is this last point, because we said that the sequential circuit test generation problem is very difficult. We want to simplify this problem into a combinational circuit test generation problem. How? We shall be seeing this. So, we look at the standard model of a synchronous sequential circuit, where there is a combination circuit part and the state variables in terms of the flip flops, which are fed by a clock, present state and the primary inputs feed to the combination logic, which generates the primary output and the next state. Now, as I said, the main problem lies because since the flip flops are inside the circuits, which are not directly connected from the output, from the inputs or outputs, directly you cannot initialize these flip flops, or directly you cannot observe the value of the flip flops. Okay? This is the main problem. So, we look at a very widely used and popular design for testability technique called scan path. Well, scan path, I will explain what it means. A non-scan sequential circuit is the conventional sequential circuit we know of. We start with a conventional synchronous sequential circuit and try to apply some rules to make it scan enabled, you can say scan path enabled. So, what are actually done? There are a few steps. The steps are as follows. First is that the flip flops, they are modified into something called scan flip flops. Then the scan flip flops are connected in a certain way such that you can use them as a configurable shift register. We shall see how. One additional primary input pin is added, and there are a couple of other pins, scan in and scan out pins for this shift register, that are also added. Let us see how it works. Okay. First, let us see what is a scan flip flop. This is a conventional master slave D flip flop, this part of it. So, you can say that I have a conventional master slave D flip flop D and a Q, this I have with a clock. What I do at the input side, I add a multiplexer. I add a multiplexer to the input side, and multiplexer select line is enabled by this extra input TC. TC stands for test control. During testing we need this, and let us say this is 0 input, this is 1 input, and the two inputs are called scan data SD and D. So, a conventional flip flop along with a multiplexer, this is called a scan flip flop, right. Scan flip flop is nothing but I am adding a 2 to 1 multiplexer at the beginning of a normal master slave flip flop, right. So, in the normal mode TC is set to 1 when D goes inside. In the test mode when TC is 0, it is not the D input, but SD goes inside. This is the only change, right. Earlier the normal master slave flip flop required 10 gates, but because of this additional thing we need 4 additional gates, it becomes 14, just remember this. Okay. Now, how do I modify our circuit? In the combination circuit, the normal flip flops were there. So, we have replaced the flip flops by scan flip flops. You see, the output of the combination logic was going to the input of the flip. So, these lines remain as it is. They go to the D input of the scan flip flop. For the scan flip flop, the upper input is D, the middle input is the test control, the middle input is TC, and the lower input is the scan data, right. And the output of the flip flop we feed back to the input of the combination circuit as usual, okay, they are coming. But some additional circuitry we have added. How we have added? We have added another scan-in input. The scan-in goes to the SD of the first flip flop. It goes to the SD of the first flip flop, and the output of the first flip flop goes to the SD of the second flip flop. This goes to the SD of the third one, and the output of the last flip flop also is brought out, and it is called scan out, one extra output pin. So, what we are actually doing here in this circuit? Just think, if TC equal to 1, this is the normal mode of operation. So, the combination output goes in, D goes in, and the output goes back, the normal circuit operation. But when TC equal to 0, the lower input of the scan flip flop are selected. So, it becomes like a shift register, you see, it becomes a shift register. So, once it becomes a shift register, you have 3 stages of a shift register, okay. They are connected like this. So, you have this scan in input connected here, and you have this scan out connected here. So, whatever input you want to initialize in the flip flop, you can shift through this scan in input, and whatever data is coming out, you can observe through this scan out pin. This is the basic idea. Okay? Just by adding these additional pins, you can easily control the flip flops, you can easily observe the value of the flip flops. Okay? Now, another thing you see, Now that we have a mechanism to completely control the flip flops, this means not only the primary inputs, I can apply any value I want here also, because I can initialize the flip flop. Similarly, on the output side I can observe not only the primary outputs, but also I can observe these. How? I can store them in the flip flops, then I can shift them out, which means now my test pattern generation I can ignore the flip flops. I can look at the combinational circuit as if all the inputs I can apply directly, all the outputs I can observe directly. So, I do not need a sequential circuit test generator, I need only a combinational circuit test generator where all the inputs I can apply, all the outputs I can observe. This is what is the big advantage that we gain here. So, now the question is, how are the test vectors applied? Now, the test generator, you see, just go back to the previous diagram once more, the PI and the present state, okay, and PO and the next state. PI and the present state are the inputs, PO and the next state are the outputs. So, the test generator will be generating the data where these will be the inputs of the combination circuit and these will be the outputs of the combination circuit. So, let us say symbolically I am just giving an example. Suppose the test generator has generated some inputs I 1, S 1, I 2, S 2, I 3, S 3 and the expected output values are O 1, N 1, O 2, N 2, O 3, N 3. Because PI is available from outside, it can be applied directly, but when you are applying this S 1, S 2, S 3, you have to apply them serially through the shift register just after setting t is equal to 0, not 1, t is equal to 0. Similarly, the next state when you want to observe the output, you have to observe them serially by configuring them as shift register and shifting them out, right. And how are they shifted in and shifted out? I am showing pictorially in this diagram. Assume this is your axis of time, this is time. So, in the beginning you set T c equal to 0 and you shift in this S 1 bit by bit through this scan in input. So, after S 1 has been shifted in, suppose it is 7 bit, 7 bits are there, then you apply I 1, because PI through PI you can apply I 1 directly. Now, you are in the normal mode, T c equal to 1. So, after doing this you can get through PO the outputs, and whatever is the secondary output N 1, the next state, that through the scan out again you set T c to 0, you can shift them out. And here you can do some parallel operation, while N 1 is being shifted out, in parallel the next serial data, this S 2, the present state can be shifted in. So, there can be parallel operations going on. Only in the last state there is no S, only N 2 is there, this N 2 has to be shifted out. And these dark places are do not cares, during this shifted in, so this PI are do not care, you can apply anything you want. So, this is just to show you pictorially how the data input and output operations take place. But the point to note is that how much time it takes. So, you can make a simple calculation regarding the total number of clock cycles that are required, right. Now, the number of clock cycles can be determined like this, n s plus 1 n c, because you see for every test vector n s, this n s denotes the number of scan flip flops. This many clock cycles will be required to shift in the data, then one cycle will be required to apply the PI and observe the output, and you will have to repeat this for so many test vectors. There are n c number of test vectors, and for the last test vectors you will have to shift out the next state. So, for that you will need another ns. This is how this equation is coming, right. So, this is one drawback of this design for testability technique, that the number of clock cycles required here will be roughly proportional to number of flip flops multiplied by number of test vectors. Okay. This is something you have to remember, that your testing time is increasing, but you are able to get complete controllability and observability of the flip flops. That is the biggest advantage you gain out of this technique. So, a very specific example, 3 input, 2 outputs and 3 state variables. So, you can just apply the, suppose these are the tests which are generated by the test generator, these are the inputs and these are the expected outputs, and clock cycle wise you can apply like this. So, first 3 clock cycles Tc will be 0, you shift in the value of the present state. After it is done, you set Tc to 1, apply the primary input, this is your I 1 and observe the primary output. Then again set Tc to 0, you observe the next state. In parallel, you also feed in the present state of the next vector. This is your present state for the first vector, this is your primary input part of the first vector, this is your present state for the second vector, this is your output for the first vector, this is your Tc, this will be your next state for the first vector. So, in this way it will go on. Okay. So, this gives you roughly an idea how the thing works. Now, just regarding the total scan testing time, let me very briefly talk about another thing, that well, we have tested the combination circuit part, but what about the scan flip flop part? There can be some faults there also. Now, there is a standard technique of testing a shift register. So, you apply a pattern like this 0011, 0011, 0011 of total length ns plus 4. So, when you apply a pattern like this, so you can see that you are going through all possible transitions 0 to 0, 0 to 1, 1 to 1 and also 1 to 0. So, you are verifying that all the flip flops are able to carry out all possible transitions. So, this is way you can test this scan flip flop. So, the total scan test length will be, this is something which you have already seen earlier, plus this. So, as an example, if there are 2000 scan flip flop and 500 test vectors, if we multiply, the test length becomes about 1,000,000. But it is not really much. You see, during testing, if you apply your clock pulse let us say at 100 megahertz frequency, then 10 to the power 6 is nothing. It will hardly take you how much, I think 10 milliseconds or so. Okay. So, this is not a really big deal, because nowadays the clock frequency is very large. So, even if you apply, you have to apply a large number of test vectors, you can afford to do that. Okay. So, talking about the scan overheads, well, you need one mandatory extra input pin Tc, but regarding the scan in and scan out, well, if you can afford to have additional pins, it is all right, but otherwise you can share them with your Pi or Po pins also, because Pi and scan in you are never using them together. Similarly, PO and scan out you are never using them together, you can share some of the pins if you want. And talking about area overhead, for every scan flip flop we said that 4 additional gates are required, and if N g denotes the total number of gates in the combination logic, it will be N g plus so many flip flops. So, originally the flip flop contains 10 gates, but in the scan flip flop 4 additional are required. So, this is your gate overhead. So, a simple example, numerical example, 100k gates and 2k flip flop, 2000 flip flops. So, overhead will be about 6.7%. This is a rough estimate. And other thing is that there are some additional delays which are included in the path, which you should also consider, because you have an additional multiplexer delay from the output of the combination circuit, because the flip flops have been replaced by scan flip flops. So, approximately 2 gate delays, and for the flip flop the fan out is increased, because earlier the flip flop output was only feeding to the input of the combination circuit, but now it is going to the input of the next flip flop also. So, increase in fan out means extra delay. So, roughly speaking, this leads to 5 to 6% degradation in the clock frequency. So, these are a few things you should keep in mind. So, we with this we come to the end of this lecture, where we have given you a brief overview about some of the design for testability techniques, DFT techniques, that can be used to handle or tackle the problem of testing synchronous sequential circuits. Thank you.